You're probably making a silent mistake on your Cambridge 0625 physics practicals that examiners penalize without fail every single year. You stroll out of the exam hall feeling absolutely confident, thinking you totally nailed the mass, weight, density, and resultant force questions. But behind closed doors, the mark scheme is quietly stripping away your hard-earned grade. We aren't doing a standard textbook review today. Instead, we're going straight into the examiner's mind to secure those hidden marks.
-2 marks, bam. That is the instant penalty you often face on simple mass, density, and resultant force practicals before you even finish reading the question. Why? Simply because you rushed the data presentation. Now, 2 marks might not sound like a huge deal, but in the incredibly tight grade boundaries of Cambridge physics, those 2 marks are literally the difference between an A and an A star, or passing and failing, and they are bleeding away purely because of technicalities in your practical data.
So we really need to ask ourselves, what is the examiner silently looking for in your practical data? I want you to think of this explainer as your personal examiner whisperer. You see, the person marking your paper isn't just checking if you memorize that density equals mass divided by volume. Not at all. They are scanning for a very specific set of secret expectations hidden deeply within the mark scheme. If you don't speak their language, they simply can't give you the marks, no matter how solid your underlying physics knowledge actually is. Okay, let's dive right into the most painful, common student mistakes that completely tank grades in practical data questions. First up, missing units in table headers. Second, rounding your numbers way too early in a multi-step calculation, which just totally destroys your final accuracy. Third, graphing axis scaling errors, picking those weird, awkward scales that make plotting practically impossible. And fourth, weak practical improvements. Writing something like, "do it more carefully" is a 0-mark answer every single time. These 4 traps literally catch thousands of students globally. And this brings us to a pretty harsh reality. Memorizing the textbook? It won't fix bad table design or awful graph scales. You can know every single formula in the forces syllabus by heart, but standard revision totally fails for the practical data sections of Physics 0625. The practical paper doesn't just test what you know, it tests how accurately and reliably you can measure, record, and interpret physical evidence. Reading a chapter on forces is definitely not going to teach you how to spot an anomaly in a resultant force graph. Now, in just a moment, I'll show you the examiner's clue that changes the pressure calculation completely. It's a hidden trap that catches almost everyone. But first, you need the framework that makes that clue absolutely obvious. Because without this framework, you'll be flying blind on every single data analysis question. Here is the foolproof 4-step high-mark framework that guarantees top-band answers on literally any explain or evaluate question. Step 1, identify the core concept. Step 2, pull the exact evidence or data from the provided table or graph. Step 3, apply scientific reasoning to connect that data to the concept. And step 4, honestly the most critical one, use precise examiner wording. If you run every single practical question through this 4-step filter, it's mathematically impossible to lose marks. Let's see how this builds by applying step 1 to density. The concept itself is simple enough, right? Density is mass per unit volume, so P equals m over V. But here's the thing. The practical examiner doesn't just want the formula. They want the specific apparatus. You absolutely must explicitly name the precise measurement tools. We're talking about a top-pan balance to measure mass and a measuring cylinder to find the volume of a liquid or an irregular solid. Using vague terms like weighing scale or beaker, that's going to cost you the mark for sure. Let's compare 2 answers side by side. A classic student response is, "the block is heavy so it sinks." Okay, can you spot the flaw there? Heavy is a totally relative term. It's not a scientific property. Instead, top band answers say, "the density of the block is greater than the density of water, therefore it sinks." See the difference? This flawlessly uses scientific reasoning and exam-safe wording. It compares the specific densities, locking in those full marks. Now, when you're designing the perfect Cambridge-style table, there are 2 massive secrets you need to know. First, your units, like kilograms and cubic meters, only belong in the headers. Never, ever write them inside the table body itself. That's a one-way ticket to losing a mark. Second, your significant figures must be completely consistent down the columns. If one mass is recorded as 0.50, the next one has to be 1.00, not just a plain 1. This exact consistency is what the examiner is hunting for. But let's escalate the stakes a bit. You've got your table, and now you plot a graph of your resultant force data. The question you have to ask yourself is your line of best fit actually reliable? When you're dealing with real practical data, you're going to have anomalies, those annoying points that just don't fit the overall trend, If you just connect the dots or force a line through an obvious anomaly, your gradient calculation is instantly ruined, and you wave goodbye to the subsequent calculation marks. To avoid that disaster, you must follow a golden rule pulled directly from a mock examiner report. It says, show the gradient triangle on your graph and make it cover at least half the drawn line. I can't stress this enough. If you draw a tiny little triangle right next to the origin to calculate your resultant force or density gradient, you will be penalized. A huge triangle proves you're taking a reliable average across a wide range of data points. So draw it big and draw it clearly.
All right, let's do a quick pause and predict. Imagine writing down calculated resultant force equals 4.5678 newtons. What is the glaring error here? Think about the actual measuring equipment you'd use in a standard school lab. Can a standard Newton meter measure to 4 decimal places? Absolutely not. No way.
So here is the examiner-style correction: 4.6 newtons. Providing an answer to a reasonable number of significant figures, which is usually 2 or 3 depending on your raw data, is a mandatory final check. If you just blindly copy out the entire string of numbers from your calculator, the examiner immediately sees a student who doesn't understand the physical limits of their own practical apparatus. Always round sensibly at the very final step. Let's look at another major trap, suggesting practical improvements. A classic zero-mark answer is simply writing, "Be more careful when reading the volume." I mean, that means absolutely nothing to an examiner. The top band answer is incredibly precise. Read the measuring cylinder at eye level to avoid parallax error. Naming the specific error, parallax error, and giving the exact actionable physical solution is what actually secures the mark. You've got to use that precise terminology. Okay, now it's time to resolve that open loop I mentioned earlier. The formula for pressure is force divided by area. Sounds super simple, right? But the massive examiner clue, the hidden trap that absolutely destroys grades, is the area unit conversion. Examiners will almost always give you the area of the object in square centimeters, but they require the final pressure in pascals, which relies on square meters. If you don't convert centimeters squared to meters squared before you calculate, your final answer will be completely wrong. Always check your area units. Let's quickly recap these quick win strategies so you have an ironclad checklist ready for your next past paper. 1. Apply the 4-step framework of concept, data, reasoning, and wording. 2. Put units in table headers only. 3. Ensure your gradient triangle covers at least half the graph. 4. Name specific practical errors, like parallax. And 5. Always check your final significant figures. Mastering these practical data secrets for forces and density will undoubtedly save your marks in this specific section. But here is the real issue. How do you apply this exact level of examiner insight across the entire Physics 0625 syllabus when you only have, say, a week left before the exam? Nailing one topic won't save you if you fall into the exact same traps in thermal physics, waves, or electricity. You need a comprehensive system to connect all these strategies instantly. To truly guarantee your grade, you need to see the entire syllabus from the examiner's perspective. So your mandatory next step is to watch our explainer on the Physics 0625 Last 7 Days Revision Map, where we reveal the common traps by question type across the whole paper. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. What hidden traps are waiting for you in the electricity section? Join us in the next explainer to find out.